Look at anything solid near you right now. Your phone, the table, your own hand. Everything you were taught about what that solid thing actually is missing something so fundamental that the physicist who found it almost buried the discovery. Not because it was wrong, because it was too strange to be comfortable. Every single electron in the observable universe, every one of the roughly 10 to the power of 80 electrons that scientists estimate to exist, every electron in your body right now, in the screen you are watching this on, in the core of the most distant star we have ever detected, they are not just similar, they are not just the same type of thing, they are, according to one of the most serious hypotheses in the history of quantum physics, literally the same electron. One particle, one entity, appearing everywhere in everything at every moment in time simultaneously. You probably just dismissed that. Good, that is actually the correct first response. Hold that skepticism, but stay here, because the argument for this idea does not come from mysticism. It does not come from a philosopher who never touched a laboratory in his life. It comes from the mathematics of quantum mechanics itself, developed by two of the most decorated physicists of the 20th century. And once you understand why the physics points here, you will not be able to look at reality the same way again. Let's talk about what quantum mechanics actually tells us. Not the version you got in school, not the version that gets rounded off at the edges to make it easier to swallow. What the data says when you remove the comfortable interpretation that gets layered on top of it. Because there is a version of quantum physics you were taught, and then there is what the equations actually show, and those two things are not always the same thing. You were taught that electrons are particles, tiny discrete, individual objects. Billions and billions of them, each in its own location, each a separate thing with its own existence and its own identity. This mental image survives from introductory physics because it feels intuitive. It maps onto how we move through the world every day, separate objects in separate places. But quantum mechanics does not say this. Quantum mechanics says something far stranger, and the strangeness is not a bug in the theory. It is the theory working exactly as designed. The first thing you need to understand is what physicists call indistinguishability. I need you to sit with this word for a moment because it sounds technical, but it is pointing at something philosophically devastating. In classical physics, if you have two identical objects, say two perfectly identical red spheres, same mass, same diameter, same color, you could in principle label them ball A and ball B. They look the same, behave the same, weigh the same, but they occupy different positions in space. And in classical physics, position is identity. Where something is tells you which thing it is. You can track them, you can follow them, you can always, at least in principle, point to one and say, that is the one I was watching before. Quantum mechanics destroys this, not partially, not as a rough approximation for very small scales, completely. Quantum mechanics says that two electrons are not just identical in the way two red balls are identical. They are indistinguishable in a sense that has no equivalent anywhere in classical physics. There is no experiment, no measurement, no observation you can perform that will tell you which electron is which. And this is not a limitation of technology. This is not us failing to build a sensitive enough instrument. The universe itself does not keep labels on electrons. There is no fact of the matter about which electron is which. The universe has not written their names anywhere. This matters far more than it initially sounds, because if electrons have no individual identity, if there's genuinely no difference between electron A and electron B, not just practically but fundamentally, then the question of how many electrons exist becomes very strange very quickly. What does it even mean to count things that carry no individual existence? What does it mean to say there are many of something, when the many have no way of being told apart, even in principle, even by the universe that contains them? Now here's where it becomes serious. In 1940, a physicist named John Archibald Wheeler had an idea so strange that he could barely bring himself to say it in a room full of people. He picked up a telephone and called his graduate student instead. That student was Richard Feynman. Wheeler told Feynman that he thought he had figured out why all electrons are identical. Feynman, who would go on to win the Nobel Prize in Physics, later described listening to Wheeler's idea and feeling something close to electric disbelief. Because Wheeler's explanation was this: all electrons are identical because there is only one electron. One electron moving through time, not just forward, backwards and forwards, zigzagging through the entire history of the universe, appearing at every point in space and at every moment in time as what we experience as separate electrons. Wheeler called it the one-electron universe hypothesis. And before you leave, understand who is saying this. Wheeler is not a fringe figure. Wheeler is not someone who wandered in from the edges of credibility. He is the man who coined the term black hole. He worked directly on the Manhattan Project. He collaborated with Einstein and Bohr. He was one of the central architects of modern theoretical physics. When Wheeler considers an idea worth proposing, it is worth examining. Here is how the mechanism actually works. In quantum field theory, every particle traces what physicists call a world line, a path through spacetime, through the four-dimensional fabric of space and time combined into one structure. Most of the time we draw these world lines going forward in time, because that is the direction we happen to experience. But the mathematics of quantum mechanics places no such requirement on reality. The equations of quantum electrodynamics are time-symmetric. They work identically in both directions. Time reversal is not a violation of quantum physics, it is an explicit mathematical symmetry of the theory. Feynman himself had already been working on exactly this. He had noticed while developing what would become his path integral formulation that in the mathematics of quantum electrodynamics, a positron behaves exactly like an electron moving backward in time. Not as a metaphor, the equations are literally identical. A positron is an electron with its time arrow reversed. Feynman used this insight to build some of the most powerful calculational tools in physics. So Wheeler took Feynman's own mathematics and pushed it one step further. He said, imagine one electron begins at the Big Bang, it moves forward in time, appears at various positions in space. Then it interacts, reverses direction in time, becomes what we observe as a positron moving backward through history. Then it reverses again, moves forward again as an electron. It does this not once, not 1,000 times, but across 13.8 billion years of cosmic history, zigzagging backward and forward through time in a pattern of incomprehensible complexity. Every single point where that one world line crosses what you experience as the present moment appears to you as a separate electron or positron. What looks like 10 to the 80 electrons scattered across the observable universe could be one electron making 10 to the 80 crossings of the present through its journey in time. The universe is not full of electrons. The universe might be full of the same electrons seen from different positions in time. Now I need to give you Feynman's objection. And I need to give it to you fully, because it is the right objection and you deserve to hear it without it being minimized. Feynman pointed out immediately that if Wheeler's hypothesis were correct, for every electron moving forward in time, there should be a corresponding positron moving backward in time. The world line that creates an electron going forward must at some point reverse and create a positron going backward. These should be equal in number. But what we observe in the universe is vastly more matter than antimatter. The number of electrons enormously exceeds the number of positrons. If the one-electron universe is real, this asymmetry needs an explanation that Wheeler's original hypothesis did not provide. Wheeler suggested that the positrons might be hidden, absorbed inside protons, or otherwise undetectable with the methods available at the time. This answer was not fully satisfying in 1940, and it is still not fully resolved. I am not going to pretend otherwise. This is an open problem with Wheeler's hypothesis. Real physics holds open problems with honesty, rather than papering over them with false confidence. But here is the context that matters. The matter-antimatter asymmetry is already one of the greatest unsolved problems in all of cosmology. We do not know why the universe has more matter than antimatter. This is not a question Wheeler's hypothesis creates. It is a question that exists at the foundation of our current cosmological models and remains unanswered. What Wheeler's hypothesis does is reframe an existing mystery. It says the asymmetry and the identity of electrons might be connected, might have the same root cause, might be different phases of the same underlying fact about reality. That is not adding a problem, that is pointing at a place where two problems might resolve into one. Let's go deeper, because Wheeler and Feynman's phone call in 1940 is only the surface layer of this idea. The one-electron hypothesis connects to something far more fundamental about how quantum mechanics actually treats particles at the mathematical level. And this is where the modern physics becomes genuinely impossible to dismiss. In quantum field theory, which is the most accurate and most experimentally confirmed description of nature currently in existence, electrons are not really particles in any classical sense. They are excitations of a field, the electron field, a quantum field that exists everywhere in space simultaneously, permeating the entire universe as one continuous structure. What we experience and measure as an electron is a vibration, a ripple, a localized excitation of this one underlying field. And here is the point that should stop you. The field is singular. There is one electron field, not one per electron, one. Every electron that has ever existed or will ever exist is a manifestation of the same underlying entity expressing itself in different modes. This is not exactly the same as Wheeler's world line hypothesis. It does not require time travel, but it says something that rhymes with Wheeler's idea in a way that is impossible to ignore. Whether you take Wheeler's approach or the field theory approach, you arrive at the same uncomfortable suggestion that what we experience as many separate electrons is a feature of how we observe and decompose reality, not necessarily a feature of what reality is doing at its foundation. Now think about what this means for the observer effect, because this is where the two ideas collide into something that most quantum physics content never makes explicit. The observer effect at its most fundamental level is the phenomenon where measuring a quantum system changes that system. When you observe an electron's position, its wave function collapses from a superposition of possible locations to a definite one. But now ask the question that the one-electron hypothesis or the single field picture makes unavoidable. If the thing you are observing and the thing you are observing with are both excitations of the same field, both expressions of the same underlying entity, what exactly is observing what? Your body is made of electrons. The atoms in your eyes are held together by electrons. The measuring apparatus is made of electrons. The electron being measured is in some deep sense made of the same stuff as the instrument measuring it. If there is literally one electron field expressing itself in all these configurations, then measurement is not an external event imposed on a separate system. The universe is observing itself through itself as itself. I know that sounds like it belongs in a philosophy seminar, but this is where the mathematics points when you stop adding walls that the equations do not require. The boundary between observer and observed, the clean separation that the Copenhagen interpretation of quantum mechanics depends on, is not in the equations. It is something we place there, because without it, the theory felt too strange to work with. The equations of quantum mechanics do not specify where the quantum world ends and the classical world begins. They do not draw a line between observer and observed. We drew that line ourselves for comfort. And the one-electron hypothesis and quantum field theory more broadly suggests that the line was always an approximation, a useful fiction, not a physical fact. Here is an experiment in active prediction. Before I tell you the next part, I want you to make a prediction. If electrons are truly separate, independently existing particles created at different times and different places across the universe's history, formed in different supernovae, ejected from different atoms, having lived completely separate causal histories, you would expect some variation. Not in their charge perhaps. The laws of physics enforce that, but somewhere some quantum fingerprint accumulated through different histories, some tiny measurable deviation between electrons that formed a billion years apart in completely different regions of space. Hold that prediction, because here is what the measurements actually show. We have measured the electron's magnetic moment, a fundamental property that encodes how it responds to magnetic fields to 11 decimal places of precision. The theoretical prediction from quantum electrodynamics and the experimental measurement agree to 11 decimal places. That is the most precise agreement between theory and experiment in the history of all of science. Not physics, all of science. And every single electron tested, regardless of where it came from or what it has been doing, gives the same measurement. Not approximately the same, identically the same to the limits of our most precise instruments. Your prediction was violated. You expected variation. You found perfect uniformity. When data violates your prediction this completely, that is not noise, that is signal. The universe is telling you something about the nature of what you are looking at. And what it is telling you is that these things carry no individual history. They accumulate no differences through separate causal paths. They are either subject to extraordinarily precise laws that eliminate all variation, or they are not actually separate things that could accumulate variation in the first place. Now here is where intellectual honesty requires us to hold three competing frameworks at the same time. Not because the answer is unknowable, but because the answer is currently unknown, and the data genuinely underdetermines which framework is correct. Anyone presenting certainty here has stepped outside physics and into performance. The first framework is the standard interpretation embedded in quantum field theory. Electrons are indistinguishable. Yes, the field is singular. Yes. But the field can support multiple simultaneous excitations, multiple ripples on the same pond. Each excitation is real, distinct, persistent. They share a substrate, but they are not the same ripple. This interpretation has no problem with the matter-antimatter asymmetry. It explains perfect identity through the uniformity of physical law. It is the working framework of the vast majority of practicing physicists. It is experimentally productive, mathematically powerful, and conceptually coherent. The second framework is Wheeler's one-electron hypothesis. One entity, one world line. Traversing spacetime in a pattern so vast and so complex that from our perspective it appears to be many. This framework has aesthetic elegance that serious physicists do not dismiss lightly. The simplicity at the foundation. One thing producing the appearance of many through the structure of spacetime itself is the kind of deep economy that has historically pointed toward truth in physics. The framework is consistent with Feynman's path integral formalism. The unsolved problem is the matter-antimatter asymmetry, but the framework stands as a serious hypothesis, not a fringe idea. The third framework is more radical and has growing support in contemporary theoretical physics, particularly in research on the foundations of quantum mechanics published over the last several years. Some approaches, particularly those influenced by David Bohm's pilot wave theory, and later by research on the holographic principle and quantum information, suggest that the very concept of separate particles is an artifact of how we decompose the quantum state. In Bohmian mechanics, there is one universal wave function, 1. It does not collapse, it does not branch. It evolves according to one deterministic equation, and what we call particles are specific structural features of this one wave function's configuration. In this picture, asking how many electrons exist is like asking how many waves are in the ocean. The ocean is one thing. The waves are a description of it. The electrons are how we describe the quantum state of one universe. All three of these frameworks are consistent with current experimental evidence. All three make identical experimental predictions for anything you could measure in a laboratory today. The difference between them is not empirical, not yet. It is ontological. It is about what you think reality is doing at the level beneath what any instrument can currently reach, and that question is open. Here is where I want to share an interpretation, and I want to be explicit that this is the line where physics hands off to philosophy. What I am about to say is not experimentally confirmed. It is a reading of where the evidence is leaning, not a statement of established facts. The perfect indistinguishability of electrons is, in my view, not something to be explained away. It is not a coincidence to be filed under laws of physics or what they are and move on. It is a clue. In every other area of science and in every domain of ordinary experience, when two things are absolutely identical, with zero variation and zero accumulation of difference, we do not say they are separate things that happen to be the same. We say they are the same thing. Perfect identity implies shared origin, or in this case perhaps something stronger than shared origin, perhaps shared nature. Perhaps, as Wheeler suggested, not just shared nature, but singular nature, because there is only one of it. Recent work in quantum information theory, and I want to be specific here, research from 2023 and 2024 on the nature of quantum entanglement across large spatial separations keeps arriving at the same uncomfortable edge from different directions. When two electrons are entangled, measuring one instantly affects the other regardless of the distance between them. We call this non-locality. Einstein called it spooky action at a distance and refused to accept it until experimental data left no alternative. We have verified it. It is real. The universe is non-local. But here is the question that the one-electron hypothesis crystallizes. If the two entangled electrons are actually one electron, if the distinction between them is a perceptual artifact rather than a physical fact, then there is no distance to cross. There is no action across space. There is no communication faster than light. There is one thing doing one thing that appears from our perspective to be two separate things correlating instantaneously. The spookiness does not disappear because we explained it. The spookiness disappears because the premise that generated it, that there were two separate things to begin with, was never accurate. I want to return to you directly for a moment because I think you came to this video because something in how physics is usually presented feels incomplete. Like the story has edges that don't quite connect, like the explanations are cleaner in the textbook than they are when you actually follow the reasoning to the end. If that is the frustration you brought here, I want to tell you that frustration is correct. You were not missing something. The presentation was missing something. And the thing it was missing is this. Quantum mechanics, taken seriously, without the interpretive padding that makes it easier to teach, does not describe a universe of separate things interacting. It describes a universe of relationships, correlations, and indistinguishable identities that behave more like one thing seen from many angles than many things happening to coexist. The question of what interpretation to hold is yours. I am not going to hand you a conclusion and ask you to accept it. The data does not support that level of certainty. What the data does support is that the question is real, the hypothesis is serious, the implications are vast, and the comfortable answer that electrons are just many separate particles, because of course they are, is not as secure as the textbooks make it look. The comfort is added, the strangeness is what the equations actually contain. You probably disagree with some of what I've said. That disagreement is intellectual work. It means you've been doing something here rather than just receiving. If you think the standard many rebels interpretation is more parsimonious, make that argument. If you think Wheeler's time reversal mechanism is too speculative to take seriously, engage with why the mathematics supports it anyway. If you think the holographic principle and Bohmian mechanics are moving in a different direction entirely, there is serious recent literature on that and I will link it below. The point is not agreement. The point is that you now have a framework specific enough to disagree with, which is the only kind of framework worth having. Here's what I want to leave you with before we get to the next step. We started this video with the assumption that electrons are many. That assumption felt so obvious it barely registered as an assumption. By the end, if this video has done what it was designed to do, that assumption now feels like a choice, like one interpretation among several, not the self-evident description of nature. That shift from invisible assumption to conscious choice is the exact movement that real physics education is supposed to produce, not the memorization of answers, the cultivation of better questions. Now, the video you just watched is not the beginning of the story. It is the middle of a structure, and the part that comes next is the part that makes this one make complete sense. Because the one-electron hypothesis does not exist in isolation, it connects directly to the measurement problem, to the question of whether the wave function is a physical object or a mathematical tool, and to what physicists call quantum non-locality, and why every proposed solution to it has so far failed, except for the ones that require us to rethink the nature of separateness itself. Those three threads, the measurement problem, the wave function's reality, and non-locality, taken together form the framework that either resolves or deepens every paradox this video raised. That is the next video. It is not background reading. It is the continuation of this exact argument. The title is cute. The reasoning picks up at the exact point where this sentence ends. Before you go there, one thing worth knowing. Your brain will retain approximately 30% of what you encountered in this video by tomorrow morning. That figure comes from memory consolidation research, and it is consistent whether you found this video easy or hard. The way you change that number is not to watch it faster next time. It is to save this video and return to the section that created the most friction, not the section that felt clearest, the one that felt most difficult. Because that section is doing the most cognitive work. The confusion is not a sign you missed something. It is a sign you are at the exact boundary of what your current model of reality can contain. That boundary is the most productive place in any education. This channel is built on a specific architecture. Each video is not a standalone fact. It is a piece of a structure where the earlier pieces are load-bearing for the later ones. The one-electron hypothesis makes more sense after this video. What comes next makes more sense after you have this one. Subscribing is not about notification preferences. It is about not arriving at video 4, having skipped videos 2 and 3. The sequence carries the argument. The argument is bigger than any single video can contain. The next video is already there. Don't pause, don't deliberate, let it play.